Okay, I hope you can hear me. Wolfram, could you give me the thumbs up if you hear me? Okay, great, thank you. Yeah, I'm very sorry that I cannot be there in person to give the lecture today. This is due to a damage of the SBB tracks at Bern. Currently, there are no trains between Bern and Zurich. And since I live in Bern, I had no chance to come to ETH today. Nevertheless, I hope that we can that I can give the lecture and you can follow it in hopefully okay quality. And then next time I will be available again. If you have questions, please, well, either ask them to Wolfram, Robin, and Stefan, or save them until next time, and then I will be happy to answer your questions. Okay, last lecture, we had a look at how a capacitor is charged through a resistor, and we calculated this characteristic curve here, the exponential approach of the charged voltage, and we saw that there's a characteristic time, the time constant, with which this is approached here. Now, the first subject of today will be basically the same circuit. We simply add one more resistor in parallel to the capacitor. And this will change things a little bit. In order to calculate what's going on, again, we have to derive a differential equation. And in order to do that, we use again the voltage law and the current law to get well, the relevant equation. Voltage law is trivial in this case here. Simply says that the voltage across the resistor must be the same voltage as across the capacitor, and that the voltage drop across this resistor and this resistor must be equal to the voltage supplied by the source. So these are these two equations here. And then together with the current law in this point, we can replace all the currents in this law with the characteristic equations. For the resistors, this is simply Ohm's law. And for the capacitor, we use the relation between current and the derivative of the voltage that we talked about in the last lecture. Now, we can replace the parallel voltage here, or the voltage over the parallel resistor, since it's the same as the voltage over the capacitor. And then we have an equation that only depends on the source voltage and the capacitor voltage and the other components, which then can be brought into the form similar to the one we had before. And we find that now where the resistor was, or the resistance of the one resistor was before, now we have the parallel configuration of two resistors here. And now I remind you that we defined the parallel, or this nomenclature here, that our parallel can be written, or that this symbol denotes this parallel connection. And then we can further simplify the differential equation. We can define a tau parallel, which is simply the time constant computed using this parallel resistor. And the tau serial, which is the normal time constant as we had it before, simply using the series resistor. And then the differential equation is easy to bring into a form that is very similar to the one we had before. And for that reason, also the solution is very similar to the one we had before. The changes are that the amplitude here is scaled by these two time constants, and that the time constant in the exponent is now this parallel time constant and not the zero time constant. Now, what does that mean? The time constant, the parallel time constant, is based on the parallel resistor, and parallel resistors are always smaller than the individual resistor. And that means that the parallel time constant here is smaller than the normal time constant. So this means that the value is reached faster. And then we have this scaling factor here in front that scales the amplitude. And this simply says that we have a reduced amplitude. So we get a reduced amplitude, but we reach it faster. And if we have a look back here, it's clear that there's a reduced amplitude because these two resistors build a voltage divider. In this example here, I've taken 10 ohms for each resistor. So we have a 1-to-2 voltage divider. The voltage at this point in steady state, when there's no current flowing through the capacitor, is just half the source voltage. And for that reason, the capacitor cannot be charged to a voltage larger than that. Okay, this is what we see here. This is the time evolution if we simply have a series resistor. So this is the case we had before. And there, of course, we charge to the full source voltage. So here, ratio between capacitor voltage and source voltage goes to 1. Now, if we have this example with the two equal resistors, then we charge only to half the source voltage. You can see that this slope in the beginning is the same, but since we have to reach only half the voltage value, we reach it much faster. So you can see that here, for example, this point where we have closely approached the voltage, this is after 4 time constants. Whereas in this case here, we achieved that already after 2 time constants. And so this is a typical trade-off that you get a faster settling behavior, but you have to give up some amplitude. Yeah. So if you think about that, you have noise in your system. Actually, you don't want to give up amplitude because this would reduce your signal to noise ratio, but sometimes it's more important to be fast than to have a high signal to noise. Okay, now where is this important? For example, if you have an amplifier, and typically an amplifier has an output resistor, and then you have a long cable. This could be, I don't know, the DSL cable that connects your modem to the connection point of the Swisscom. So this could be a long cable. A long cable means that it has a significant resistance and a significant capacitance. And if you want to send fast pulses through such a cable, then this can be made impossible if there is a long time constant. Now, by adding one more resistor here on the receiver side, which could, for example, be an oscilloscope or even your, as I said, your modem, adding one more resistor here can make the time constant much shorter, which means that you can send faster signals, which then, of course, is good for fast communication. Okay, now let's have a look at the original RC circuit just with a series resistor here. And one particular aspect of it, namely power. So the question is, what is the power that has to be supplied by the voltage source in order to charge the capacitor? And how much power is dissipated in this resistor? And so abruptly charging the capacitor from 0 volts to the voltage of this voltage source. So imagine it was discharged, and at time equals 0, we connect the voltage source. And then, of course, we get the time behavior we have seen already. Now, this is the voltage of our source. The And then you see, okay, the 1 here is the full source voltage. And in the beginning, there is a term that we subtract from this source voltage. And this makes the slow charging of the capacitor. If we, and of course, the voltage that is missing here must be the voltage that is dropping over this resistor. So the voltage over this resistor is simply the same term, just taking this part here. And in order to get the power that is dissipated in the resistor, we need, of course, the power formula, which is, for example, voltage squared divided by resistance. Could also be current squared times resistance. But since we deal with voltages here, we take this one. And so we can write the time dependence of the power simply by squaring this and dividing by the resistor. Now, of course, in order to get the total energy, we have to integrate over the power. So, well, theoretically from 0 till infinite time over this quantity. The source voltage and the resistance don't depend on time, so we can pull this in front. And then we see that this is an integral over an exponential function for which this nice identity exists. And so we arrive with this solution. And now we remind ourselves that the time constant tau was r times c. And so this can be simplified, and we find that the total energy that is needed to charge the capacitor is 1/2 c times u squared. Now, this is the exact same formula for the energy that is stored in the capacitor. And well, you see that 1/2 of the total energy supplied by the source is dissipated in the capacitor, in the resistor, and the other half is stored in the capacitor. Interestingly, this dissipated energy is independent of the value of the resistor. So if you have a small resistor, then in the beginning you have a large current, and you charge the capacitor very quickly. If you have a large resistor, then it takes a long time. The current is smaller, but in the end you have dissipated the exact same energy. Now, this is true if you charge the capacitor, if you try to charge the capacitor abruptly. There are better ways to charge a capacitor, more energy efficient. But if you do it like that, then you waste half the energy in the resistor, which is unavoidable. And the other half can be used to charge the capacitor. Yeah, so the total work then, of course, is the sum of the two, and this is c times u squared. Now, this calculation is important for circuits where you want to abruptly charge the capacitor, and then let's say you discharge it again. And so if you do one charge-discharge cycle, then you have, well, charged the capacitor, and then if you discharge also the other half of the electrical work is dissipated in the resistor on the discharge cycle. So the total energy that is dissipated for one charge-discharge cycle is given by this expression here. And now imagine this is a capacitor in a processor, and charging and discharging are the logical ones and zeros in the processor. And at the clock speed of the processor, we change the state of the capacitor. Then, given a certain frequency, well, once per cycle of this frequency, we dissipate this amount of energy. And so the power that is dissipated is the frequency times the capacitance times the voltage squared. And well, this is a good model for the power dissipation in processor chips, CMOS circuits. And it's the reason why our processors in our computers and smartphones cannot go to very high frequencies, because the power rises linearly with the frequency. And now, if you have worked with computers over the last decades, the capacitance could be reduced quite significantly because the structures in the chip became smaller and smaller. The voltage was reduced as much as possible, since this enters this power in chronologically. And for that reason, the frequency could be increased quite a lot. But this is fundamentally the limit why it cannot be increased very easily to much higher frequencies. Okay, so that's so far about capacitors. Let's come to inductors. Now, inductors are, Spulen are in principle the counterpart for capacitors, with the, well, I mean, they are like really the counterpart, that everything that in a capacitor is a voltage, in a coil or in an inductor is a current. And so for, and the inductor actually, well, doesn't want the current to change, in the same way that a capacitor doesn't want the voltage to change. Yeah, it needs an effort from the outside, a current flowing through the capacitor to change the voltage of the capacitor. And in the same way, it takes a voltage difference over the coil or inductor to make the current that goes through the inductor change. And the fundamental reason for that is that the inductor, if a steady current is going through it, there is a magnetic field inside. And if you want to change this magnetic field, then a current is induced that opposes the change. And so there's a voltage difference building up over the inductor that opposes the change of the current. Now, in analogy to the capacitor, we can define this fundamental differential equation, that the voltage that is needed to have a change in current is proportional to this change in current, and the constant of proportionality is the inductance. Inductance is measured in Henry, and Henry is volt-seconds per ampere. Yeah, so as I said, if there's no voltage across the inductor at constant current, the actor acts against current changes. So it tries to smooth out current changes. Inductances add if we put several inductors in series, and they add reciprocally if we add them in parallel. Yeah, as I said, an inductor reversibly stores energy in a magnetic field, and we can compute this energy using this characteristic equation in the exact same way we did for the capacitor. And we also find a very similar formula here, simply replacing the role of the voltage with the role of the current, and of course the role of the capacitance with the role of the inductance. Okay, now inductors are used for high frequency applications. They are also used for low frequency circuits, especially the frequency spreading filters in loudspeakers. They are efficient to suppress electromagnetic interference, for example, in power supplies. And of course, they are used if you couple two inductors magnetically as transformers. Well, inductors are used with reluctance because they are relatively expensive to produce. It's only a limited potential for miniaturization. And the fundamental reason for that is that in silicon integrated circuit technology, you can produce capacitors but not inductors. So for an inductor, you have to wind a coil somewhere, and this is always like a mechanical job. Whereas a capacitor can be simply made as surfaces in an integrated circuit. Yeah, so for that reasons, inductors are less common. Electronic engineers tend to avoid them. And another reason is that it's possible to replace inductors with capacitors, for example, using the gyrotor circuit. Okay, now fundamentally, inductors are really important. So let's have a look at the same situation we had with the capacitor. So the basic charging experiment, and in case of an inductor, this is a circuit where we want to drive a current through this coil. And we have to give this current, well, an alternative route, and for that reason, the resistor in the problem has to be in parallel to the coil. Again, we use Kirchhoff's laws to derive the important equations. So the current law in this junction here, and the voltage law that simply tells us that the voltage across the resistor is the same as the voltage across the inductor. Okay, then we can use the defining equation of the inductor to identify the voltage over the resistor with this term, and then replace all currents. No, sorry. Oh no, this is simply this equation multiplied with resistance. And then we identify that this is Ohm's law for the resistor, which is this voltage, and this voltage we can replace with this expression. Which gives us, well, after forming it a little bit, again, a characteristic differential equation, which looks pretty much exactly the same as the one for the capacitor. In analogy to the capacitor, we define a time constant, and this time it's L divided by R. If we put the time constant here, then it looks exactly like the differential equation for the capacitor, and we can solve it in the same way. So we get a solution that looks like this, and we see that in the case of an inductor, the current also exponentially approaches the source current after a certain time. So this means in the beginning, the current flows through the resistor here, because the inductor is not really conducting. And then as the current in the inductor here rises and rises, the effective resistance of this becomes smaller and smaller, and in the end, all the current goes through the inductor. Okay, now the next thing we can do is combine a capacitor and an inductor. And the simplest circuit is simply, well, basically connecting a capacitor and an inductor in a loop. I remind you that these two ground connections mean that this is connected. And again, we use Kirchhoff's voltage and current law. The voltage law, I mean, in this case, is super simple. It simply says that these two voltages are equal. The current law says that the two currents are equal. And then we simply say that the voltage over the inductor is given by this term depending on the current. We know that this current is the same current that goes through the capacitor. And so we can use the characteristic voltage, the characteristic equation of the capacitor to replace that, and in the end get an equation for the voltage of the capacitor. Now, in this equation, since we have used these characteristic equations with the derivative, we have used them twice. So first to convert a voltage into a current, and then again to convert a current into a voltage. We get the second derivative of the voltage across the capacitor. Now we define the resonance frequency, eigenfrequenz, as 1 over LC, and then it's easy to guess what the solution of this equation must be. We have a function, or nicer written here, we have a function. If we derive this twice with respect to time, then we have to get the same function with a scaling factor. And now have a look in our differential equations before, there was always a negative sign here. But in this different equation, there's a positive sign. So that means that the scaling factor here has to be negative. And the scaling factor is squared. So the only way to have this negative is if we have a complex exponent. Or using the laws of well, how cosine and sine is derived. You know, if you build the derivative of a cosine, you get minus a sine. If you build the derivative of minus the sine, you get minus a cosine. So there is where the sine comes in. Okay, so this is the general solution. And it means that this circuit oscillates and that the energy oscillates back and forth between the capacitor and the inductor. This all happens at a given angular frequency, omega 0. Okay, now why is this oscillating? Imagine at the beginning the capacitor is charged, and then this means that there's a voltage difference across the capacitor. Now this wants to discharge through the inductor. And so the inductor, there's a current induced in the inductor, and this current is slowly rising until the capacitor is discharged. But now we have a current going in the inductor, and as I said, the current, the inductor doesn't want that the current changes, so it keeps the current going. It pushes out well, current through the other direction and charges the capacitor in the reverse way. And then again, the capacitor is charged as soon as the current from the inductor is used up, and then the process goes on in reverse. At this point, I want to make an important comment that if we write frequencies in these equations here, it's always an omega. And so this means it's an angular frequency. And the unit of an angular frequency is in principle radians per second. And since that's not so convenient to write, people often also write inverse seconds. The important comment is that the unit hertz, which in principle is the same as inverse seconds, is only used for frequencies and not for angular frequencies. So if you write down an angular frequency like this one, something that can directly go into the argument of a cosine or sine, you have to multiply the normal frequency with 2 pi. Since you need to go to an angle of 2 pi to do 1 revolution of the angular frequency. This now is a problem if you want to give a value, and this is often mistakes are made. So the safe way to specify a value is that you say, okay, I specify omega divided by 2 pi, then I can say this is like, for example, 10 Hertz. Or you can specify that omega is equal to 2 pi times 10 Hertz. Multiplying this with 2 pi then is equivalent to something like 62 inverse seconds. Okay, so there's a factor 6 approximately that can be wrong, and if you find somewhere that the factor 6 is missing, it's probably that you have forgotten to either multiply or divide with 2 pi. Okay, now the next thing I'd like to get into is the, well, LCR circuit, German the gedämpfte Schwingkreis. And so what we do is we have the inductor, the capacitor, and in between we add a resistor. And this means that now the energy cannot circle indefinitely between these two, since every time there's a current going through the resistor, some of the electrical power is dissipated. And so for that reason, it's called gedämpfter Schwingkreis. Gaining the differential equation to calculate this is straightforward as we used before. So first of all, we use the defining equation of an inductor. Insert this one into the voltage law. Then we use again the defining equation of the capacitor. Insert that, and then now you see that we get 2 times this voltage of the capacitor. As before, we get the second derivative for the coil, and we get the first derivative for the resistor. And now we have to define 2 things. The resonance frequency, again, is 1 over LC. And we have a time constant here, and this is, again, R times C. And then using those, we can rewrite the differential equation in a nicer form. And here you see that we have the part that we had before. Then we have this additional part, which now will drastically change the behavior. So the solution is, of course, equivalent to the damped pendulum, and we distinguish 3 domains. The underdamped case is when the resistor is small enough, and the condition is that R squared must be smaller than 4L over C. And then we get a cosine wave with an exponential decay in front of it. And this is shown here as the blue curve. So you see we get an oscillation, but with an amplitude that becomes smaller and smaller. And as I said, the reason for that is that in every cycle, a bit of the electrical energy is dissipated in the resistor. And for that reason, the amplitude becomes smaller and smaller. Now, at the defining critical resistance, the solution looks like this. And this is the critical damped case. The critical damped case is the fastest approach of 0. And this might be interesting when you want a system to, for example, a regulator, to put a system very quickly into a certain state. Then it's desirable to be on this critically damped case. If you try to be faster than that, then probably it will oscillate. And if you try to be slower than that, you are not as fast as you could be. Yeah, not as fast as one can be is the overdamped case, where you approach 0 just much, much, much slower. Okay, I hope this is visible. For some reason, these plots with a black background are difficult to see. So what I did here is, again, a SPICE simulation with a voltage source. The voltage source is pulsed, and this SPICE command here tells it to generate pulses from 0 volts to 1 volt with a period of 1 microsecond and a pulse width of 500 nanoseconds. And this is the white curve that you see here. This is the input voltage, simply going up and down. And then you see what happens in the 3 different cases. So in the underdamped case, it's oscillating. So that means that every change initiates a new oscillation, and then it tries to find its steady state. And if we would wait long enough, this oscillation would die out and it would just stay at this level. In the critical damped case, we quickly approach the new value. And then here again, we approach the new value. In the overdamped case, you see that we never actually reach the new value since the waveform switches before this long time constant here can reach the value of the pulse. Okay. Yeah, you will see in the exercises how to conduct similar simulations. Okay, in order to discuss now the following subjects, I should introduce the decibel scale. Probably you've heard already about decibels, but I would like to introduce it formally. And it's important to specify amplification or suppression factors in electrical circuits. So the unit bel is used for a ratio of 2 powers or 2 energies, and they both have to be of similar. So for example, you could have an input power and an output power of an amplifier, and then you could quantify the amplification of the amplifier by dividing the output power through the input power. This gives you a dimensionless quantity, and then we take the logarithm with base 10 of that quantity. Now, numerical values are almost always given as a decibel, so like a decimeter. This is simply a tenth of a bel. So in order to get the numerical value, we have to multiply with 10. And in this case, now the unit of this quantity is decibel, dB. Now, as we've seen before, the power in an electrical system scales as the current squared or like the voltage squared. And now, if you don't want to measure the power that comes out of, for example, your function generator, but you want to know what the amplitude of the voltage is, then it's often more convenient to work with voltages. And for voltage or current-like signals, one can say for amplitudes, we can replace this power here. And we've seen that there is a scaling factor between power and voltage squared, or power and current squared. Depending on the circuit, it must be some kind of resistor. But since it's the same scaling factor on top and on bottom, it drops out. So this is what I mean when I say it must be 2 powers of similar type. And so we can simply replace this ratio of powers with the ratio of voltages squared. And now the square can be taken out and it leads to a factor 20 instead of a factor 10. So if you give the same amplification factor can be specified using this formula as a ratio of powers, or using this formula as a ratio of voltages. It's numerically the same value in decibels. And so if you're given a value in decibels, you can choose if you want to know a power ratio, then you have to invert this formula, or if you want to have a voltage or current ratio, and then you have to invert this formula. It's also possible to specify absolute values in decibels. And here I have examples for current, voltage, current, and energy. And the way that is done is that in this fraction, the reference value or if you want to specify an absolute value, you don't have a ratio. So the reference value is whatever is given behind the decibel unit. So if it's dBV, it means that it's a quantity divided by 1 volt. And since those are amplitudes, you have to use the factor 20 here. If it's a dB milliamps, that means it's a current divided by 1 milliamp. This gives a dimensionless quantity. Since current is also an amplitude quantity, we have to use the factor 20. You could specify an energy in dB joules. This means that the reference value is 1 joule. And so we divide the energy by 1 joule. Since this is an energy quantity, we use the factor 10 here. This can be done basically with all units that you like, and it's common in electronics to use those. There are some conventions that deviate from this system. The most important one is dBm. Decibels are very often used to denote power. And so if you want to give a quantity with reference to 1 milliwatts, the watt here is saved. So dBm means a power relative to 1 milliwatt. And since it's a power or energy unit, you have to use the factor 10. The other exception that I know of is sound pressure. You probably have heard about sound being specified as decibels. And there one doesn't say what the reference quantity is, and the reference quantity are 20 micropascals as the sound pressure. And I think this is the hearing threshold of an average human. So 0 decibels is what you can hear, like the smallest sound you can hear. Okay, so let's give a few examples. If we have 0 decibels, this means that the ratio between output power and input power is 1, or between output voltage and input voltage is also 1. Now, plus 3 decibels, this is approximately a factor 2 in the power ratio, and consequently a factor square root of 2 in the voltage ratio. Accordingly, 6 decibels is a factor of 4 in the power ratio, and is a factor of 2 in the voltage ratio. 20 decibels is a factor 100 and a factor 10, respectively. 40 decibels is a factor of 10,000. So for the power, it's simply counting the zeros and adding a 0 here. And it's the square root of that, again, for the voltage reference. Now, you can specify negative decibels, and then what you mean is that something got smaller. Yeah? If you have an attenuator, then the output power is a small fraction of the input power. So for example, a minus 20 dB attenuator has an output power which is 1/100th of the input power, or an output amplitude which is 1/10th of the input amplitude. Okay, so I hope that's clear. Yeah, this brings us to the break for this lecture. And I will continue at 1:45. So thank you. Okay, let's continue. I hope the sound still works. Okay, now that we've introduced the ratio of amplitudes and powers, we can take one more important step, and that step is circuit analysis for complex networks. And so typically what you would do is that you have a time-dependent voltage. This is your source. And then you have a network here that consists of capacitors, resistors, and inductors. And we call them the linear components. And at the end of the lecture, I can give the correct reason why we call them linear components. Last lecture, someone asked me, and this will become completely clear as soon as we have introduced complex impedances. Yeah, so the goal of network analysis then is to get the time-dependent behavior of the whole network, so all voltages and currents in all components. And of course, this can then lead to a quite complicated system of differential equations. Now, it's possible to numerically solve that, and the simulation software SPICE that we will use, and which comes in many different varieties, does exactly that. And so this is one approach that will be covered in the simulation exercises, and you will do that quite a lot. Now, here in the lecture, I want to focus on a different approach. And this one is to decompose the signal into Fourier components. So take this complex signal apart, deconstruct it into different frequencies, and then compute the behavior of the network simply for sinusoidal input voltages with an arbitrary frequency. And then you can compute the time dependence of the components by transforming back into the frequency domain. So we can change between the time domain and the frequency domain using inverse or forward Fourier transforms. So it's equivalent if we can describe the behavior of the network as a function of frequency, then describing it as a function of time. So here's an example of a signal that is decomposed into Fourier components. The signal is a step function from -1 to 1 with a given period. So here you see one period is just 1/2 positive, 1/2 negative, very symmetric function. And for this one, it's easy to write down the Fourier components in terms of sine waves. It's only sine waves because here at 0, it's 0. If we would shift this in time a little bit, then also cosine components would show up. And then you see that all the odd frequency multiples of this fundamental frequency appear in the Fourier series. You also see that the more Fourier components we use, so the blue is simply the first Fourier component, then the orange gives the first and the second, and then you see we already approach this behavior much better, where the first is simply one sine wave. If we take this into account, then we already get something that approaches the square-like structure here. If we now take the fifth, then we get the green curve, and this approaches, of course, this signal even better. And now if we take more and more Fourier components, the match between the input signal and the decomposition into Fourier components will become better and better. Okay, so what do we have to solve? If a sinusoidal signal with frequency omega is applied to the linear passive network, the current and voltage in each component of the network will also be sinusoidally oscillating with the same frequency. So this is a really important statement because it allows us to treat all the frequencies differently. And basically, this can be taken as a definition of what is a linear component. If you excite it with one frequency, and then all the what happens at the same frequency. So a linear component does not change the frequency of this the signal. This is not true if you, for example, use send a voltage through a diode, which has a complicated characteristic curve. Then it will produce all kinds of frequencies. Yeah. So for a linear component, if we have a sinusoidal input signal with a given frequency, then current and voltage in each component of the network will have the same frequency. And this makes it easy to describe the whole network simply for this one frequency component. So there's no mixing between different frequency components. And so we can introduce a short hand for writing that our voltage is like some amplitude, u0 times a sine wave at a given frequency. And so we call this simply voltage of omega t, where omega t is the argument of the sine here. And similarly, we can define a shorthand for the current that is oscillating. This is an amplitude I0, and then again the sine wave in a very similar way. Using these two definitions, we can write Ohm's law simply by applying it, so to say, for each moment in time. And then, of course, what comes out is that the sinusoidal voltage is produced by the sinusoidal current. And so we can simply identify the voltage and the current in Ohm's law with these time-dependent voltage and current. Now, this is a simple multiplication with R. So this means that the current and the voltage oscillate with the same phase. So when this sine wave goes up, also this sine wave goes up, since there's no phase difference between the two. And then, well, we say they oscillate in the phase. Okay, now let's have a look what happens with a capacity. we have this characteristic equation of a capacitor. Again, the current is scaling constant, the capacity times the time derivative of the voltage. And now, if we assume that this voltage is a sinusoidal, has a sinusoidal time dependence, then we can simply calculate the current by building this derivative. And then, of course, the current is simply given by a cosine wave, since we had to build the time derivative of the sine wave. And of course, this voltage here, and the omega factor comes from the chain rule. So we also get this in front of the expression now. So the frequency scales the current. Yeah, and so in case of a capacitor, the larger this frequency, the larger the current. Now, if we use that the cosine of alpha is, of course, the same as a phase shifted sine wave with a positive phase shift of pi half, we can write that the time dependence of the current, again, is a copy of this signal. And then we can use our shorthand to capture this phase shift. And then we get this dependence here, that the time dependence of the current is, well, our voltage signal with a different phase shift here, with a constant phase component. Now this we can bring into the form of Ohm's law. And so we find that we have a time-dependent voltage that is equal to some form factor times a time-dependent current. And this is actually why we call a capacitor a linear component, because for a given frequency, current and voltage have this linear simple proportionality. And then we find that what was the resistance before is now replaced with, well, this expression here, which depends on the frequency and the capacitance. And of course, this makes it much easier to calculate what the, well, the relation between voltage and current in a capacitor is, since before we had to solve a differential equation to do that. And now we simply have to apply a phase shift and multiply with a scaling factor that looks like this. Okay, now for the inductor, we can do the exact same thing. Now, of course, we use the defining equation of inductors. Here we have to integrate it. Again, by integrating the sine wave, we find a cosine plus an integration constant, but this we can set to 0. And so we find again an dependence of the current voltage dependence. Here, the voltage given as a scaling factor times the current, where we have to add a phase shift to the current. Okay, and again, this factor here is in the place where in Ohm's law there is the resistance. And now this will allow us to define a more general Ohm's law. Yes, here one can remark that the voltage peaks at an earlier time than the current, and for the capacitor it was the other way around. And so here we summarize all those. So for sinusoidal signals, capacitors and inductors show the same multiplicative relation as in Ohm's law. And so for a resistor, you simply multiply with R. For a capacitor, you multiply with 1 over omega C. For an inductor, you multiply with omega L. So this gives the amplitude. And then there's a phase factor. For the normal resistor, it's 0. For a capacitor, it's minus pi half. For the inductor, it's plus pi half. Now, the definition of the sign here is a bit difficult, depending on, how you write it. And so what I like to memorize is that for a capacitor, the current needs to be before the voltage, which is clear since in order to get voltage into a capacitor, in order to charge a capacitor, first a current has to flow. We have to carry charge carriers to the capacitor, and this is only possible with a current. On the other hand, for an inductor, there's voltage before current. The inductor doesn't want to conduct a current, and only if we apply a voltage, we can make a current going slowly. So there we always have voltage before current. Okay, and now we can identify these two things that we have to do. We have to scale with a factor, and we have to apply a phase shift. And both can be done using multiplication with complex numbers. So complex numbers, characterized in their polar form, have a modulus and an angle. And when we multiply with a complex number, we multiply with the magnitude and add the angle. And this is exactly what we have to do in order to define an extension of Ohm's law with which we can treat capacitors and inductors. So here we find the calculation rules that we need. And so what we can do is now we can define a complex resistance, which then is called impedance, which replaces the normal resistance in Ohm's law. So let's do that. So if you represent an impedance as a complex number, this is really elegant to calculate with sinusoidal signals. It's actually so common that electrical engineers naturally decompose any signal into frequency components and simply think about what a single frequency component would do in your system. And then in the end, if you have to care about the time evolution of a signal, you can either transform back into the time domain, or what is more common, you simply know that if a certain frequency component is not transmitted through your signal, that then in the time domain, this will have a certain effect, and we will have a look at that. Okay, so let's define the complex impedances. The complex impedance Z for the resistor is simply the resistance. It's the same thing as the normal resistance. And the units are, of course, volts per amperes, same as ohms. For the capacity, we have seen that we have to multiply with a factor of 1 over omega C. And then the I, the complex unit in the denominator here, produces the necessary phase shift. And this is, of course, the same thing as minus I times this fraction. Now, what about units? The capacitance is ampere seconds per volt. And this we multiply with inverse seconds. So this is amperes per volt in the denominator, so volt per amperes, same as ohm. So this complex impedance, if we build the norm, has the same units as the normal resistance. And then for an inductor, we saw that our factor has to be omega times L, and here we have to have this positive I to get the correct phase shift. And again, the units work out that if we take the absolute value of this, we have to multiply inverse seconds with volt seconds per amp, which again is ohm. Now, this means that for complex voltages and currents, we can write down this Ohm's law with the complex impedances. Now, the question is, what does it mean to have a complex voltage and current? Okay, first let's have a look at the complex impedance. So, of course, we have a complex number can be decomposed into the real and imaginary part, shown here on the real and imaginary axis. And the magnitude then, of course, is the length of this vector in this plane, simply calculated here. And the angle with respect to the real axis, this is important, can be calculated with the arctangent of imaginary over real part. And for the calculations we are going to do, the magnitude and the angle are more important than the real and complex components. Okay, and now what is easy to do if you want to characterize the behavior of a complex network, it's typically done by plotting the amplitude and the phase separately as a function of frequency. Now, if we have an inductor, as you've seen just now, there is a positive imaginary part, so it will be some number that looks like this. If we have a capacitor, it has a negative imaginary part, so it will be a vector pointing down in this plane. Okay, let's come to an example. So this is the important thing where we identify the real current that we have in our world with the real part of an exponential oscillation that can be written like this. It should be clear that the exponential function e to the I omega t, if we take the real part of this, gives us a cosine. And the amplitude is simply a scaling factor that is not affected by this. So in this example here, I've chosen an amplitude of 4 milliamps. And then, of course, we get a sine wave that oscillates between -4 and +4 milliamps. So this amplitude is measured from 0 to the peak. In electronics, often amplitudes are also measured as peak values. So from here to here, and then of course you just have to double this value. Another important quantity is the effective current, which is this peak current divided by the square root of 2. And the effective current defines how much power is transmitted by this signal. So it's the DC current which has the same amount of power as this sine wave. And if we now take an example that the oscillating current with an amplitude of 4 milliamps and a frequency of 50 hertz passes through a 1 microfarad capacitor. So we can find our angular frequency as 2 pi times 50 hertz. Here comes the factor 2 pi. Since the 50 hertz is a normal frequency and we want an angular frequency, we have to multiply with 2 pi. We can simply define the impedance of the capacitor, 1 over I omega c. C is given, omega is given, so this we can calculate. And then we can simply write down the time dependence of the voltage is, well, impedance times time dependence of the current. And now, since we want a real world voltage, we can immediately take the real part of that and put in the complex definition of this current. So this extension into the complex plane of the cosine wave. And then it's easy to multiply this oscillating current with the impedance. We simply add the two exponents of the E function. We get this. And then we identify this with a phase shifted cosine. And so going from well, this to this is quite easy if we use the complex impedance. And I mean, especially it's possible to do it without solving differential equations. And then we define the peak voltage that goes through the capacitor as the magnitude of the impedance times I0. So if we are just interested in magnitudes, we can even stop caring about these complex impedances or complex definitions of oscillating signals. We can simply multiply the amplitude of the current with the magnitude of the impedance, and we get the amplitude of the voltage. So in order to go from the 4 milliamps to the 12 volts, we simply multiply the 4 milliamps by, well, we divide through 2 pi 50 hertz and the 1 microfarad. And then we get to 12 volts here. The same we can do for effective voltages, since the effective voltages are simply scaled with a factor squared of 2. The same holds for effective voltages. Yeah, so here you see, again, this signal at time equals 0, it's a cosine wave. The current is at its maximum. We calculate for the voltage, the phase shifted cosine wave, as you see here. And as I said, for a capacitor, current comes before voltage. So first the current peaks, and then a quarter of a period later, 90 degrees later, the voltage has its peak. Okay, so this should give you like an example how this is used. In reality, what's really important is this equation here, that you can go from this amplitude to that amplitude simply by multiplying with the magnitude of the complex impedance. Okay, now for complex impedances, since they observe the Ohm's law, we find pretty much the same rules as for resistors. So for series connections, we simply add them. For parallel connections, we add them reciprocally. And now one can define the admittance, the same as the conductance for a normal resistor, which is simply 1 over the impedance. And for admittances in series, they add reciprocally, and in parallel, they add simply. So this is completely equivalent to resistors. Okay, now let's do the frequency dependence of an RC circuit. Well, here is one of the points where I say, okay, this is like a voltage divider, but now look, now we have two components connected in the same way as a voltage divider. So if this would be a resistor, it would be easy to calculate that this is a voltage divider, which simply gives an output voltage that is a fraction of the input voltage. Now, if we treat this as a complex impedance, we can use the formula for the voltage divider also with the complex impedances. And this allows us immediately to write down that the output voltage is the input voltage times this scaling fraction here. Now, of course, let me remind you, the impedance of the capacitor is given by this term. Impedance of the resistor is simply the resistance. Now, what is often important for a system is the transfer function, and the transfer function is the output voltage divided by the input voltage. And so if we take this expression here and we divide the output voltage by the input voltage, what remains is this fraction. In the fraction, we can replace those values, and then we can write it a bit nicer. And then you see that the transfer function is given by a really simple, nice expression. Now, this would be a lot of work to get if we would solve the differential equation and try to arrive at this result. Now, it can be written even nicer if we define our resonance frequency or characteristic frequency. And then you see it's simply well, a fraction where this part here is dimensionless. And that makes it easy to scale to different applications. Okay, now, as I said, it's really important to know the magnitude of this quantity. So the magnitude of the transfer function is the magnitude of this complex number here, or 1 over the magnitude of this complex number. And this is simply well, the sum of the squares of these two, and then taking the square root. And for the phase, we find that this is also a function, an arctangent function of this quantity. Okay, so let's plot this. So as a reminder, the magnitude of the transfer function is the magnitude of the ratio of output voltage divided by input voltage. We have seen that we can write it this way. We can replace the RC with a characteristic frequency, and then this becomes dimensionless. And then one can call the dimensionless for that is well, in principle applicable to every situation, since it can be scaled to the problem, to fit your problem. So again, the characteristic frequency or cutoff frequency, again, this is an angular frequency. So if we want to convert it into the usually used frequencies in Hertz, we should not forget the 2 pi. This is 1 over RC. So it's called Grenzfrequenz, Übergangsfrequenz, Eckfrequenz, minus 3 dB point, critical frequency. This has many names. And it's the frequency at which the transmitted power drops to 1/2. So this is a ratio of amplitudes. So if we want to calculate what the ratio of powers is, again, we simply square these two. And so a magnitude squared is the ratio of transmitted powers, and this goes to 1/2. Okay, as I said, using the transfer function, which is a ratio of 2 amplitudes, and this x variable, which is a ratio of 2 frequencies, 2 angular frequencies or 2 real frequencies, makes everything dimensionless, and thus the graphs that I show here are universally applicable. So if we have a look in linear scaling, then you see that the magnitude of the transfer function drops with increasing frequency according to this formula. And if we go to x equals 1, so this means that the frequency is equal to the Grenzfrequenz or critical frequency, then we dropped to 1 over square root of 2. And this means that the square, so the power transfer function, goes to 1/2. You also see that at larger frequencies, this drops off like 1 over x. Okay, now I've drawn the exact same 2 functions in a double logarithmic plot, and then they look quite different. And now you see why the RC circuit is called a low-pass filter. At low frequencies, the transfer function is 1. So this means the signal goes through with the same amplitude. And then it drops off. And now this 1 over x function in a double logarithmic plot becomes a straight line. And you see that we approach this straight line. And for larger frequencies, it drops off as 1 over x. Now, a drop-off proportional to 1 over x, the first power of x is called a filter of first order. Okay, this is the order plot of a low-pass filter. So this is the function we've just seen. And this is the phase. And what does that mean? At small frequencies, the output and the input oscillations are in phase. And at larger frequencies, they are out of phase by pi12, so by 90 degrees. Okay, what I forget to say is that also this is the linear scale here, and this is the decibel scale. And typically the attenuation of such a filter is given in decibels. So if you want at 100 hertz, 40 decibels of suppression or minus 40 decibels of amplification, then this is the right filter for you. Yeah. And of course, this is an approximation to say that signal components with frequencies smaller than the cutoff pass through the filter, because this is not completely true. You see here, it starts to drop off already a little bit before the cutoff frequency. But then after the cutoff frequency, the frequencies or the components are more and more suppressed. Yeah, the low-pass filters are important. They are used to suppress interfering signals. And they are generally make a signal more smooth. Okay, we can do the exact same thing also for the CR circuit. So here we have replaced the position of the capacitor and the resistor. And we do the exact same thing. We say, okay, this is a voltage divider. We replace the resistor and the capacitor in this formula. And we already know that we can write the transfer function now, which again is the ratio between output and input voltage, as this ratio. And this again can be simplified and looks like this. Looks of course different, since this is a completely different behavior. Now, the magnitude of the transfer function, as we've seen, is an important quantity. And if you follow through with the math, you find this function, which is very similar to the one that we had before, except that before we had a 1 up here, and now we have an x up here. Okay, with the same definitions of the time constant and the critical frequency and the dimensionless scaling or frequency parameter x. Now, if you have a look how this goes for large frequencies, so for large values of x, then this here for large values, this goes to 1. Yeah, so this high frequencies can pass through this filter. For small frequencies, this one here is basically 1, and it's proportional to x. So for small frequencies, the amplitude of this transfer function is proportional to x to the plus 1, and so this is also a first order filter. Doubling, so if you look at small frequencies, then doubling the frequency leads to a doubling of the amplitude. And doubling of the amplitude is 6 decibels. And so for that reason, this is called also a +6 decibel per octave filter steepness. And 6 decibels per octave is characteristic for also first order filters. Okay, so here we have the border plot of the RC circuit. As I said, it rises linearly But in the double logarithmic plot, you wouldn't see that it's linear, but it really rises linearly here and then settles off and lets pass through the higher frequency components. The phase shift looks the same as with the low pass filter, simply that we go from 0 not to minus 90 degrees, but to plus 90 degrees. Okay, high pass filters, they have a zero transfer function at DC, so at zero frequency. And so they are used to suppress DC values. If a signal passes through such a DC suppressing filter, only the alternating current remains, and so it's called then an AC signal or AC coupled if you use a high pass filter to couple a signal. And this is, for example, the case for your oscilloscopes where you can switch between DC and AC coupling. And so if you activate AC coupling, nothing else happens than just activating a high pass filter between the input of the oscilloscope and the display and recording part. Okay, so let's have a look at the transient behavior. So until now, we have looked at these filters, the RC circuit and the CR circuit, low pass filter and high pass filter, in the frequency domain, and we've seen that certain frequency components are suppressed. And now, what does that mean for a time series? And if you take such a standard square wave as the input signal, then a DC coupled filter, a low pass filter, simply makes it a bit slow to reach the value. This we have already seen, this slow approach. And then if you go back, it also makes it slow. An AC coupled circuit, if you have such fast signal components here, they go through and then they decay quickly to 0 again. And now if you would stay at this high value for a long time, this signal would stay at 0 for a long time. So if the signal does not change, there is 0 output on the CR circuit. So AC coupling is kind of differentiating that when you have a fast change in the component, then you get an output. And if the value does not change, even if it's at a very high amplitude, you get 0 on the output. Of course, if it changes with a different sign, then you get also a different sign as the output of the high pass filter. Yeah, so this is then a different direction of the time derivative. Okay, let me show you one more thing, and this is important for the exercises. So let's take an example where we have a signal source with an internal resistance, and then we go through a long cable which has a capacitance to the oscilloscope input at a similar situation we have looked already today. And concrete values are, for example, 15 picofarad for the capacitance in the oscilloscope, a mega ohm for this internal resistance of the oscilloscope, and then a meter of cable can add again like something like 45 picofarads. Okay, and then of course this internal resistance together with these two capacitors builds an RC circuit, and so this prevents us from recording fast signal changes. Now there is a very nice solution to this by introducing two more components here at the beginning of the cable. So this is at the Tastkopf or oscilloscope probe. So this can be integrated into the part that is used to connect the oscilloscope cable to your circuit. And if you integrate another resistor and capacitor into the probe, then you can drastically improve the performance of the oscilloscope. And so let's have a look how that works. Now, let's say that the 90 picofarad is the combined capacitance of the cable and the input of the oscilloscope. The 1 mega ohm that we see here is the internal resistance of the oscilloscope. And now if we put a 9 mega ohm resistor in parallel with a 10 picofarad capacitor, then we will see that this circuit avoids the RC behavior. And in order to calculate that, it's best to look at the admittance, so 1 over the inductance of this part of the circuit and 1 over the inductance of this part of the circuit. It's easy to see what happens at the extreme cases. Now, if we go to really, really small frequencies, then the capacitors play no role. They have basically infinite impedance, and so there's no current going through the capacitors. So this is purely resistive. And then we see that this is a voltage divider. Okay, if we, for the moment, set this resistor here to 0, this is simply a voltage divider with these two resistors. It's 9 mega ohms to 1 mega ohm, which gives us a dividing ratio of 1 over 10. Now, if we go to really, really high frequencies, then the resistors don't play a role because the capacitors here are much more conductive than the high values of those resistors. So we can do the calculation simply for the capacitors. Again, we see this is a voltage divider. We write down the voltage divider formula. We put in the impedances of the two capacitors. And then we see that the two capacitors are chosen in a way that this also results in a 1 to 10 ratio, divider ratio. And so we get the exact same behavior at low frequencies and at high frequencies. And this is great. Then the probing frequencies becomes independent of frequency. So we get a flat transfer function. Now the question is, what happens at intermediate frequencies? And here it's best to calculate, as I said, with admittances. So we have to use the conductance of the resistors and the admittance of the capacitor for one case and for the other case. Then we can write down the formula for the voltage divider, put in all the values, and then we see this simplifies to this form where this part cancels with that part. So independent of frequency, this is a dividing ratio of 1 over 10. And this has two important advantages, that the transfer function is independent of omega, so constant amplitude transfer function for all frequencies, and that it is real, so we have no phase shifts. Yeah? And both things are important if you want to do a measurement with your oscilloscope. There's one more advantage, that the load for the source becomes in resistance becomes higher. Yeah, since now we have a load of the series connection of the parallel, the probe resistor and the oscilloscope resistor, which gives 10 mega ohms instead of 1. And the capacitive load also becomes smaller, since here we have the two capacitors in parallel. And so it's 9 picofarads instead of 90 picofarads in this experiment. And so even if the internal resistance here is not 0, because of that effect, we get 10 times faster rise times and 10 times smaller amplitudes. Okay, this simulation here shows how the behavior deviates if we do not match the perfect conditions quite correctly. So you see, for the perfect conditions, we need 10 picofarad in this probe capacitor here. And now what I did is I did a different kind of analysis using SPICE. I told it to do an AC analysis where per decade I want 100 frequencies from 10 Hertz to 10 gigahertz. Yeah, and then you see, for the perfect value of 10 picofarad, the amplitude is constant and the phase is also constant, the orange curve in both graphs. Now, if we deviate from the values, then you see that the amplitude changes slightly here by 10%, and that we get a few degrees of phase shift. Yeah. And for that reason, it's possible to tune the probe to be perfectly aligned with these conditions. Okay, yeah, this is the content for the lecture today. I hope you have fun with the exercises, and I hope that next lecture I can be there in person again. So have a nice day. Thank you.